Hello, we're going to start our study of Chapter 6, which is confidence intervals. And we're going to cover all four of these sections. So let's go ahead and get started with our discussion about confidence intervals for the mean. Now, confidence intervals for the mean when sigma is known. So we've got basically the big idea of what is a confidence interval. Throughout this entire section, or actually throughout this entire chapter, we're going to have one goal. And our goal is going to be to estimate a population parameter. That's unknown. So let's put in here an unknown population parameter. Now, do you remember what constitutes a population parameter? I've written it here. So, population mean, population standard deviation, variance, and we're going to introduce a fourth parameter, which is the proportion of success, right? So the goal for this entire chapter is to estimate a population mean when you don't know what the actual mean is, right? There's no point in estimating the mean if you actually know the mean, right? So we're estimating it because it's unknown. And whenever you're estimating, you want to be as accurate as possible, but there's going to be some error involved, right? So anytime that you have an estimate, that means that you're going to have error or a possibility of error involved. So our goal, of course, is going to be how do we give a really good estimate and minimize our chance of error, right? Okay, so we've got two kind of ways to estimate an unknown population parameter. The first is with just a single number, which is a point estimate. And the second way is to give a range of values. So that is an interval estimate. Confidence intervals are our interval estimates. So we're going to learn about point estimates and interval estimates. And the last thing we'll learn is a formula, how to use a formula to tell us how large our sample needs to be in order to have, in order to have a certain amount of error or minimize the amount of error. So if we say, hey, we want to estimate this population parameter and we need to be within, we need to be within 5 percentage points or something like that, then how large of a sample do you need to take in order to make sure that you're within that error bound that you've set for yourself? Okay, so let's talk a little bit about point estimates. Now, point estimates for mu. So that's what we're working with for this section, right? So section 6.1 is all about population mean. So we're estimating population mean. And a point estimate, if I were to just ask you what's the best way to estimate a population mean, then you would probably answer me, best way if you don't know the population mean would be to take a large sample, a random sample that's representative as best as possible, and then use that sample mean. And that's kind of like the best way, that's the best you can do in terms of estimating the population mean. So this is in fact what we would do. So the most unbiased point estimate of the population mean is the sample mean. So let's do this example here. So in this example, we're supposed to find a point estimate of the population mean, and the population here is, what is our population? Let's actually write this down. So reading this, what is the population? The population is all number of hours worked by all grocery store employees in a county. So now, because it's impossible or, too expensive to gather all of the numbers of hours worked by all grocery store employees in that county, what they did was, what the economics researcher did was just to collected a sample. So collected a sample of the hours worked by 40, a random sample, that's actually important, random sample of the hours worked by 40 employees from several grocery stores in the county, right? So that way it's more representative as opposed to just taking all 40 of your data points from the same store. It's good to, kind of mix it up a little bit. And we want to approximate
It's
mu.
7:15.
Thank you. We want to approximate mu, which is the population mean. That's what we want to approximate. And the idea is that we're going to approximate it using the sample mean. So how do we do that? We've got our numbers here. And what you need to do now is pause the video, enter these numbers into your list one. So go to Stat, go to Edit, clear your L1 if you need to. So Stat, and then go to Edit and enter the data into L1. And then once you've entered the data into L1, 30, 26, 33, 26, 26, 33, 31, 31, blah, blah, blah. I've done all of that. Now I go press Stat again. Let me use a different color here. So I press Stat, and then I'm going to go over to Calc. So go to Calc, and then one var stats. So it should be your number one. Go to one var stats, hit enter. Your frequency your list is going to be L1 frequency list. You can leave that blank. Hit calculate, and then I get all of my stats about this list, right, of 40 data points. And in particular, I'm able to see that my X bar is 29.6. So mu, which is approximately X bar, which is 29.6 hours. So this is our initial estimate for how many hours grocery store employees work in this county. We would say based off of our sample, we can approximate that the average number of hours is 29.6 for the whole population. Okay, so that is a point estimate. Now let's look at and compare that with an interval estimate. Instead of a point estimate, which is just one single number, an interval estimate allows us to give a range. So instead of saying, oh, the mean is approximately 29.6 hours, we're able to say, oh, the mean is somewhere in between 31.7 and 27.5. So do you see that left endpoint here is 27.5 and the right endpoint is 31.7? This would be a way to give an interval estimate. Now, when you give an interval estimate, you've got a possibility of error. Just like when you give a point estimate, you've got a possibility of error. But with an interval estimate, you've got less error because it's more likely that the value is somewhere in this interval rather than what's the likelihood that the value, right, that we're trying to find, which is mu, what's the likelihood that that value is exactly equal to 29.6? It's probably not exactly equal to 29.6, right? So that's the benefit of an interval estimate, is that you're giving a range, and so it's more likely that you're actually capturing the actual value that you're trying to estimate. But now here's the dilemma. How confident do we want to be that the interval estimate contains the true mean? Because if we wanted to be 100% confident, we could say, oh, mu is somewhere in between 0 and 1 billion. I don't even know if that's 1 billion, but yeah, 1 billion. Now that would be a very good estimate, right? And we're definitely confident that the true value is somewhere in here, but this is a useless estimate. Why? Because there aren't even 1 billion hours in a month. right? So we know for sure that mu is going to be a positive number. It's not going to be negative, right? So even though we're confident, 100% confident, this isn't a helpful estimate. So the key is to give an interval estimate that is helpful. And the smaller we make the estimate, the interval estimate, right, the narrower our interval, the more likely it is that the interval doesn't contain the actual population mean, right? So it's a trade-off between accuracy and having the interval actually contain the population mean. So this brings us to this next concept, which is level of confidence. So your confidence level is denoted by C. So let's go ahead and put this in here. So C is your confidence level. And we're going to see C a lot. And C is a probability that the interval estimate contains the actual population parameter. So remember before we said it's very easy to come up with an interval where there's a 100% probability that your actual value is in that interval. But usually by the time you have 100% confidence, your interval is so large that it's not useful. Okay? So how do we find our critical values? We're going to need the critical values to help us to determine the size of the amount of error, the margin of error that we'll allow, right? So how do we find the critical values? You take your level of confidence, whatever your level of confidence is, and you need for the level of confidence to be the area between your two critical values. So now we'll need to do several examples so that you can see how to compute your critical values, not using the standard normal table, but using your calculator. So using the TI-84 to find the corresponding z-scores. And I can tell you that here's the bottom line. The idea is this. We'll know C. So C will be known. And we want to find our critical values, ZC, negative ZC and ZC. That's the notation for the critical value is ZC. So if C is known, so this area is equal to C, right? And now we'll use symmetry and inverse norm to calculate our critical values. Okay? So if this area in the middle is C, so if this area is equal to C, then what is the area in these tails? What's the area in this right tail and this left tail? That area in the right tail and the left tail has to be 1 minus C. Because remember, the area underneath the distribution has to be equal to 1. So all of the area together is equal to 1. And so if the area in the middle is C, then the area of the tails is 1 minus C. And so now due to symmetry, that means that the area of just one tail is going to be half of 1 minus C. Okay, so you'll see that's what is being explained in this picture. This picture is trying to say that this area is half of 1 minus C, and the area in this left tail is half of 1 minus C. So if we want to compute our critical value, all we need to do is say negative ZC is going to be inverse norm. And then what is the area? The area is 1/2 1 minus C. And our mean is 0 and our standard deviation is 1 because this is a z distribution. Right, so then we would put into our calculator inverse norm of whatever, because remember C is given, so C is known. So this is a known value. We'll get some number, a negative number, and then that's how we know our critical values. So let's do this example here. Now, if the level of confidence is 90%, here's how we interpret this. So level of confidence is 90%. That means C equals 0.9. Okay, so level of confidence, remember, level of confidence is C, right? So level of confidence is C. So if C is 0.9, then this area right here is 0.05, and the area in the left tail is 0.05, right? So on my calculator, if I put in, let's go to second distribution. So go to second vars, okay, which will give us distribution. And then go to inverse norm. So mine is number 3. And then for area, if I put in 0.05, and for mu is 0, sigma is 1, hit enter, enter again, then I get negative 1.648533626, which we can round up to negative 1.645. And that tells me that my critical values are negative 1.645 and positive 1.645. Okay, so just in case you haven't seen this notation before, let me point out that this plus and minus means 1.6, oh, you can barely see that. So the plus and minus means 1.645 and negative 1.645. So we always have two critical values when we're working with our confidence intervals. And again, we're going to use the critical values to determine how long our intervals should be, because the critical values are going to play into our margin of error, and the margin of error plus the point estimate together give us our confidence interval. Okay, so let's introduce this notation here. So the sampling error, this is a definition, and this might be a, I can't remember if this is on one of the homework questions, but sampling error is the difference between the point estimate and the actual population parameter value, right? So if your population parameter is mu, then your point estimate is X bar, because remember, the sample mean is going to be the best estimate of the population mean. So here we are. So for mu, the sampling error is this difference right here. So we can say sampling error equals X bar minus mu. And what this tells us is, this tells us how far off is your point estimate from your actual, right? Your actual value that you're trying to find. So that is what the sampling error tells us, is how far off is your point estimate. Okay. Now, one of the things to notice is that the sampling error varies based on the sample that you take, because when you take different samples, you'll get different sample means, and so you'll get different sampling errors. Okay. The margin of error is the greatest possible distance between the point estimate, and the value of the parameter it is estimating for a given level of confidence C. So the margin of error, here's our formula actually for the margin of error. The margin of error is E equals, now ZC is your critical value. This is a positive critical value because remember we have two critical values, a positive one and a negative one. So positive critical value. And this is your sampling error. Not your sampling error, your standard error. And remember we learned about standard error last chapter, in chapter 5. The standard error is the standard deviation of your sampling distribution of sample means. So the requirements is that number 1, your sample is random, and number 2, your population is normally distributed, or n is greater than or equal to 30. So if either of these conditions holds, right, so if your population is normally distributed or n is greater than or equal to 30, then we know that the sample distributions, the sampling distribution of sample means,
7:30.
Thank you, is normally distributed by the central limit theorem, right? So that's why we need for one of these conditions to be true, because then we can invoke the central limit theorem to say, okay, we know the standard deviation of the sample means, and we can use that to compute the maximum, the greatest possible distance between that point estimate and the actual parameter. Let's do an example. So this example is of finding the margin of error. Okay, so we want to use the data about the grocery store employees to find the margin of error for the mean number of hours worked by grocery store employees. So this is our mu, right? This is our mu, and we want to find the margin of error. So the first thing we can do is we can write our formula. So our formula is that E equals ZC times our standard error. What is the standard error? Is going to be sigma over square root of n. Now, first thing we need to do is to find ZC. So to find ZC, remember that ZC is based off of our standard normal deviation, the standard normal distribution, 1 and -1. And we're told in the problem that C is equal to 0.95. So if C is equal to 0.95, then that means we're going to have all of this area here. This area is equal to 0.95. And that means that the leftover area, how much is this? This is going to be area equals 1 minus 0.95 over 2. And the same with this area. Area equals 1 minus 0.95 over 2. So now what is 1 minus 0.95 over 2? 1 minus 0.95 over 2. Okay, so that is 0.025. So I can erase this to be 0.025. I can erase this to be 0.025. Okay, and now my goal, I want to find out what is that number, because that's going to give me my critical value. So question mark is just going to be inverse norm. My area is 0.025, and my mean is 0. My standard deviation is 1, because I'm working with the standard normal distribution. So let me go to second vars, and then inverse norm, and for area, 0.025. For mu, 0. For sigma, 1. Paste, enter. So I got negative 1.959963986. Okay, so negative ZC is negative 1.9. We can round it up to 1.96, right? So ZC is 1.96, and this is what I wanted. because I need this for my formula here, right? So now I know that my ZC is 1.96. Okay, now what is my sigma? It's here in the problem. So in the problem it says, assume the population standard deviation is 7.9. So that means sigma is going to be 7.9. And then what is in, well now how many data points did I have in the original data set? 40, right? Because it was 40 employees that were interviewed to get their number of hours that they worked. So my E is going to be 1.96 times 7.9 divided by the square root of 40. And I get 2.448. Okay. So that is my solution. E equals 2.448. Actually, it's 2.35365. So we can round that off to 2.45. Okay. And the interpretation of this is that we are 95% confident that the margin of error for mu is about 2.45 hours. Okay. So notice that the margin of error depends on the confidence level. Okay. So if we'd had a different confidence level, then we would have had a different critical value. And the critical value is part of our formula for the margin of error. So it's appropriate that we include that we're 95% confident. Okay, so now let's talk about creating confidence intervals for population mean. This is what we came here to do, basically. And we'll have, here's what we do. You take your point estimate. So you take your point estimate, X bar, and your confidence interval is going to have a left endpoint and a right endpoint. The left endpoint is when you take X bar minus your margin of error, and the right endpoint is X bar plus your margin of error. So notice that E is always positive. E is always a positive number because when you are, this is the formula for E, right? So we just gave the formula for E. Your critical value is always positive. It's never a negative number, so always positive. Sigma is always positive. And of course, N is always positive, so the square root of N is also always positive. So E, your margin of error, is always positive. So we can use it as a distance, and it's the distance. The endpoints for the confidence interval are determined by the margin of error and your point estimate. Okay? So the probability that the confidence interval contains mu is C, assuming that the estimation process is repeated a large number of times. And so we'll talk a little bit about this later. But what does the question is, what does the confidence level tell us? Well, the confidence level tells us how many times. So if we were to repeat this process of taking sample after sample after sample and building confidence interval, confidence interval, confidence interval, what's the likelihood that the actual value would be in our confidence intervals? It's determined by C. That's what the C is telling us. Okay, so I want to point out here, so here's something else I want to point out, is that we've got three different ways to, let's go up here. We've got three different ways to, three different notations for confidence intervals. The first one is right here, right? So this is one way. Another way is to write X bar plus minus E. Okay. And then the third way is using interval notation, which would be X bar minus E, comma, X bar plus E. So I wanted to point out that we have three different ways so that if you're looking, at other sources or you're reading article journals, you're not confused, right? So we've got three different ways, three equivalent ways to express confident intervals. So people will use interval notation. This one right here, X bar plus and minus E, this is used for like in polls, so you'll say it's this plus or minus 3%, right? So you'll, plus or minus 3 percentage points, whatever. So it's that plus or minus 3 percentage points, that's giving you your margin of error, okay? And then the last one here is kind of this, this long drawn out, the longest one here. So all three of those, you can use them interchangeably. Let's go ahead and do an example. And what I want to do is I want to talk about how to use technology to find a confidence interval. Now, when we find a confidence interval for a population mean, I don't know if hopefully you're able to see this. I've posted a video. So if you look in the modules, under TI 84, so if you look on the modules in Canvas, and if you're not sure where to find this, you just email me. You can look under TI 84 videos, I think is what it's called. There's a page, TI 84 videos. And I put up a video or a link to a video that shows you how to use your TI 84 to compute critical values and also to compute confidence intervals. So right now I just want to go over the notation. Here's what we're going to do. We're going to go to Stat, go over to Tests. So how do you get to Z interval? Go to Stat, and then click over to Tests. We're going to be hanging out in tests for the rest of the semester. And then for mine, it is, on my calculator, it's number 7, Z interval. Okay? And then with Z interval, you've actually got kind of two different ways that you can give it information. You can either, so I'm going to highlight this. If you have a bunch of data, right, and you want to find a confidence interval and you're given a bunch of data, you can input the data. Or if you're given stats, you can input the stats. So you'll have this option, this INPT stands for input. You'll determine what kind of information you want to feed your calculator. And then based off of that, it'll spit out the confidence interval, right? So the big deal is you've got to know what you're in, you've got to know your point estimate, and you've got to know your population standard deviation. And the last thing you need to know is your confidence interval, right? So with those 4 pieces of information, then you click calculate and it will spit out the confidence interval for you. Now, we can also, here's the long drawn out way, and this is the way that the book does it. But again, we have technology, so I'm encouraging and assuming that you use the technology, which is number 1, to verify that sigma is known and that the sample is random, and either the population is normally distributed or n is greater than or equal to 30. And then you figure out n and x bar, and then find the critical value ZC, then find your margin of error. The reason why I'm saying use your calculator is because tables will not be provided on the exam. So you want to make sure that you know how to use your calculator and not just relying on being able to use tables. And then once you have your margin of error, you can compute your left endpoint, your right endpoint, and then you can put your interval together. But again, it's a lot faster to just put the data into your calculator and use technology. So let's do this example here. Construct a 95% confidence interval for the mean number of friends for all users of the website. All users of the website. Of what website? I think this is an error, so let's do, instead of the mean number of friends for all users of the website, let's do the mean number of hours.
It's 7:45.
Thank you. Mean number of hours worked by all grocery store employees. Okay, so let's do that. Now, if we recall, so first we're just going to use technology. So go to stat, go to tests, go to Z interval. Okay, and now here's what we need. And then so for input, you're going to click stats, highlight stats, and press enter. And now we need to know sigma, we need to know X bar, we need to know N, and we need to know C level. So that's the confidence level. Okay, and then it says calculate. Okay, now it should be really easy for us to figure out the confidence level. It's going to be, C is going to be 0.95. And now N, as you recall, was 40. What was our X bar? Do you remember our X bar? Our X bar was, let's see here, 29.6. And we were told that the sigma was 7.9. So sigma 7.9 and X bar is 29.6. Let's put this in. So sigma 7.9, 29.6. Now something that you'll notice is that if you used stat and edit, right, and then entered the data into L1. So if you entered your data, remember those 40 different hours into your calculator, and then, 1var stats to get the X bar. When you go to Z interval, the X bar is automatically going to be populated with the X bar from that 1var stats. So that actually kind of saves time. The calculator is kind of anticipating that you're doing a confidence interval for the data that you entered in earlier. So that's good. It'll also populate the N. So your N should actually already be populated with 40, your X bar, and it's going to try to populate sigma, but it's just going to use S bar, right? Or not S bar, but S. It's going to use S because that's the best it's got to go off of, right? So you're actually going to need to enter in 7.9 there. And then for C level, put in 0.95, calculate. And here's what should show up: 27.152, 32.048. And then X bar equals 29.6, N equals 40. So it reminds you of the X bar and it reminds you of N, just in case you forget or something like that. And this is your confidence intervals right here. So it's using the notation, it's using this third notation here. So this is what your TI-84 gives. If you notice that this is exactly the same as what we would get This is the same result. Copy, let's see here, paste. So if we were to take that our X bar is 29.6 and E is, what do we compute for E? We computed E was 2.45 or 2.448. 2.448. So if we do 29.6 plus 2.448, right? So X bar plus E, which is 29.6 plus 2.448, 32.048. So this is your right endpoint. And likewise, your left endpoint is going to be X bar minus E. This is going to be your left endpoint. So what does the calculator do? The calculator computes E and then computes X bar plus E, X bar minus E, and spits out the confidence interval for you. Okay, let's do another example here. The college admissions director wants to wishes to estimate the mean age of all students currently enrolled. So it takes a random sample of 20 students, and the mean age is found to be 22.9. years. From past studies, the standard deviation is known to be 1.5 years, and the population is normally distributed. So that's good. So the first thing we want to do is we want to verify that our population is normally distributed. Okay, construct a 90% confidence interval of the population mean age. So what is the information we've been given? Well, we've been given that C is equal to 0.9. Okay. We're also told that the standard deviation is known to be 1.5 years. So that means sigma is 1.5. Okay. So now notice this is sigma is 1.5, not S is 1.5. So we're given the population standard deviation and the mean age of the sample. So the sample mean is 22.9. So X bar is 22.9. And the last bit of information that we're told is that N is equal to 20. N equals 20. So on the calculator, we go to stat, tests, Z interval, and then we want stats. So my sigma is 1.5. My X bar is 22.9. N is 20. And my C level is 0.9. Calculate. And I got 22.348, comma, 23.452. So the interpretation is that with 90% confidence, we can say that the mean age, so let's put here, so with 90% confidence, we can say that the mean age of college students at that college is between 22.3 and 23.5 years. Okay. So here's the deal. Whatever the true value is, whatever the true mean is, right? So mu, who knows what it is? right? Whatever it is, either it's in this interval or it's not, right? And what we're saying is that if we repeat this process of taking a sample of 20 students, calculating that sample mean, and then constructing the confidence interval, right? If we keep doing that a whole bunch of times, like if we were to take 100 samples of 20 students, 95 of those confidence or 90 of those confidence intervals would include the true value of mu, and like 5 probably wouldn't, or sorry, 10 probably wouldn't, right? So that's the idea, is that 90% of the confidence intervals would contain the true population mean if we were to repeat this process of sampling and creating a confidence interval, sample, create a confidence interval, right? If we repeat that a whole bunch of times, about 90% of those confidence intervals would include the true mean. Okay? So, So it looks like I wanted us to solve this on the graphing calculator, and the other way was to use critical values. So if we're going to use critical values, it is not so bad. Let's just copy, command copy. We're going to copy this information, paste. And for critical values, here's what we need. We need to find E, and our left endpoint is going to be x bar minus E. Our right endpoint is x bar plus E, right? So this will be our confidence interval. So the formula for E is that E is equal to our critical value times our standard error. And the standard error is sigma over the square root of n. So we've got sigma and we've got n, so we just need to find our critical value, ZC. So to find ZC, here's what we do. Remember, it is based off of the standard normal distribution, which has 0 in the middle, 1 here, -1 here. And since C is equal to 90%, so we've got something like this much right here. So this area is 0.90. And if that's 0.90, then I automatically know the area of these little tails, because these tails, that area has to be 0.05, and that area has to be 0.05, because all of the area has to add up to 1.0. So to figure out what is this value here, this value, I'm going to need to use my inverse norm. So inverse norm, the cumulative area is 0.05. My mean is 0. My standard deviation is 1. So on my calculator, I go to second vars for distribution, inverse norm, area 0.05, mean is 0, sigma is 1, paste, and I got -1.6448, right? So negative ZC is -1.6448. So then ZC must be 1.6448, which we can round up to be 1.65. And I know that we actually computed this critical value before. I just wanted to show you how to do it again, because sometimes it's challenging for students to figure out how to compute the critical value. So I wanted to get in some extra examples for you. So back to our formula over here. So we know our critical value is 1.645, and our sigma is 1.5, and n is what's n? N is 20, so we need 1.5 divided by the square root of 20. And what will that get us? 1.645 times 1.5 divided by the square root of 20. So we'll have 0.55175. Okay, so this is E. So x bar plus E is going to be, what's x bar? 22.9. plus 0.55175, which is 23.45. Okay, and then x bar minus e is 22.9 minus 0.55175, which is equal to minus 0.551749, 22.348. 34825. Okay, so if we did everything correctly, this number should be our right endpoint. So let's put this here, 23.4517. And this bottom number should be our left endpoint, so 22.34825, comma. Now, if we really did everything correctly,
it's 8 o'clock.
Thank you. Then we should get here exactly what we got with the other one. So let's just verify. So 22.348, 22.348, yep. And then 23.452, yep. So doing it either way gave us the same answer. And of course, it's a lot faster to do it using technology. But I just wanted to go through that so that you could see it. Now, just to repeat, mu, your actual value, so this is your actual value that you're trying to estimate. Your actual value is a fixed number. Either it's in a confidence interval or it's not, right? So you're trying to come up with a confidence interval, which is your estimate. And either mu is in it or it's not. So it's incorrect to say there's a 90% probability that the actual mean is in this value, because either the mean is in there or the mean is not in there, right? What's correct is if we repeat this process of sampling 20 students and creating, each time we sample, we'll get a new point estimate, which will be our sample mean, and then we'll create our own, our new margin of error, right? And so we'll have a whole bunch of confidence intervals, a confidence interval that corresponds to each sample that we took. If we do this a whole bunch of times, then approximately 90% of those intervals will contain the true value. So here's a picture, and imagine that this is your mu, right? So imagine you were to find out that your actual value is mu. Sometimes you'll have a sample, and that sample, the point estimate is so low that mu is not in that confidence interval, right? But that's okay, because we're not saying that mu is in every confidence interval. What we're saying is that 90% of the time, if we were to keep doing this, we would have the actual value in our confidence interval. Okay, so here's the key phrase here. In the long run, 9 of every 10 intervals will contain the actual value. Okay. Now, the last thing we want to do is, suppose you're given a confidence level and a margin of error, and you want to find out what is the minimum sample size that's needed. Well, we've got our formula for E. E is ZC. Let me kind of erase this. How do we solve for N? Well, E, our margin of error, is our critical value times the standard error. So if we want to solve for N, all we have to do is literally solve for N. So it'll be square root of N is equal to ZC times sigma over E. So then now square both sides, right? If I square both sides, then that means that N is equal to that squared. So if you know E and you know your critical value, right, because you know your confidence level and you know sigma, and you want to find N, you can figure out how large N needs to be just by solving the equation for N, okay? And now if sigma is unknown, you can estimate it using your sample deviation, provided that you have a preliminary sample with at least 30 members. So let's do an example here. You want to estimate the number of friends for all users of a website. How many users must be included in the sample if you want to be 95% confident that the sample mean is within 7 friends of the population mean? Assume the sample deviation is about 53. Okay, so we know we have our formula, and our formula that we need to use is N equals, let's see here, our critical value times sigma over E squared. So N equals our critical value times sigma over the error squared, right? Now, that means we need to know what is our critical value, what is sigma, what is E, right? So, you want to estimate the mean number of friends. How many users must be included in the sample if we want to be 95% confident? So if we want to be 95% confident, that means that C is equal to 0.95. And so what is our ZC? Well, let's see here. We can do our little trick. It's not a trick. It's a computation. So we say, okay, this middle part, the middle area is 0.95. Okay. And the area on the end has to be 1 minus 1, so let me do it on my calculator, 1 minus 0.95 divided by 2, which would be 0.025. Okay, so that value, that z-score, find the z-score is what we're trying to do, right? So that z-score is going to be inverse norm. The area that I want to put in is 0.025. My mean is 0. My standard deviation is 1. So what is that? Second vars to get inverse norm. My area is 0.025. Mean is sigma. Standard deviation is 1. Paste. And I get negative 1.95996. Okie dokie. So we'll say that is about negative 1.96. So my ZC is going to be equal to 1.96. So I figured out ZC. ZC is going to be 1.96. What is my sigma? This is in the question. The question says assume the sample standard deviation is about 53. Now remember, when can I replace sigma with S? I can replace sigma with S if I have a preliminary sample of at least 30 members. So what I'm going to do is in my mind I'm going to say make sure that my answer is at least 30 because I'm going to replace sigma. I'm going to say sigma is approximately S, which is equal to 53. And I'm doing that assuming that my final answer for N is going to be at least 30. Okay, so if it turns out that I get a number that's less than 30, I'm going to say, hey, I need to bump it up to 30 because that was part of my assumption when I did my computations. And the margin of error, you want to estimate the mean number of friends. How many users must be included in the sample if you want to be 95% confident that the sample is within 7 friends. So here is the key phrase here, is within 7 friends. Right? Well, not the friends part. Is within. Right? So this is our hint that we're giving information about a margin of error. Right? Within, plus or minus, those are keywords. So our E is going to be 7. So now I can plug all of that into my formula and get N equals, so I need 1.96 times 53 divided by 7 and square it. So I get 220.2256. This is definitely more than 30. So I don't need to worry about having a sample size that's less than 30. Because so far, I'm saying that my sample needs to have at least 220.2256 people, right? So at least 220.2256 people. But what does that mean to say that you need at least 220.2256 people? That means you need at least 221 people. So 220 people is not enough. Is not enough. N needs to be at least 221. Okay, so you want to be, because we're so used to saying, hey, if we're rounding, why wouldn't we round down to 220? And the answer is you need at least 220.2256 people. So you need more than 220 people, so you have to round up. Okay, so your sample size is going to be 221. All right, so we've done a lot this section, just kind of introducing us to the calculator moves and to critical values. And I think that once we work through some later sections, 6.2, 6.3, and 6.4, some of these things repeat, a lot. So it'll make more sense as we do more problems and as we get deeper into the material. All right, that's it. Thank you.